Welcome. Today, AB Physics 2, Unit 9.1, the kinetic theory of temperature and pressure. 7 multiple choice questions. But the goal isn't really the answers. The goal is to see why gases behave the way they do. From the inside out, let's go. Microscopic origins of the pressure. Picture a single molecule mass m zipping back and forth horizontally between two walls of a cube. Side length L. Every time it slams into the right wall, it bounces off elastically and heads left. Time between consecutive hits on that wall is delta T. The question, what is the average force this one molecule puts on the wall? Pause and think before you answer. So now we can see the answer is it's A, mv squared over L. So here's a trick. Force is impulse over time. So each bounce flips the molecule's momentum from positive momentum, mv, to negative momentum, negative mv, of course. So going to the right is positive, going to the left is negative. So the molecule loses 2 mv. Why? Because when it's going to the right, it has to leave or lose 1 mv first to become 0. Then loses another negative mv to become negative mv. So it actually lost 2 mv, its momentum. Anyways, and by Newton's third law, the wall gains 2 mv. So now, how often does this happen? The molecule has to cross the box and come back, a round trip of 2L, traveling at speed v. So delta T equals 2L over v. Divide impulse by time, so 2mv divided by 2L over v. So the 2's cancel and the v's combine, and out pops what? mv squared over L. That's pressure being born one collision at a time. Okay. So now question 2. 2 sealed containers sit in the same warm room. One holds 2 moles of neon. The other holds 1 mole of krypton. Krypton being roughly 4 times heavier per atom. After a long time, both containers reach the room's temperature. Now compare the average translational kinetic energy of a neon atom versus a krypton atom. Different masses, different counts. Does any of that matter? So the answer is, of course, C, equal. Notice what the equation for average kinetic energy actually says. Kinetic energy average equals 3/2 kBT. That's it. No mass, no moles, no volume, nothing but temperature. So if both gases share temperature, they share an average kinetic energy. The heavier krypton atoms are simply moving slower to compensate. Same energy, different speeds. Question 3. Root mean square speed. So, if heavier atoms move slower at the same temperature, by how much? Gas A has molecular mass capital M. Gas B has 4m. Same temperature. What is the ratio of their RMS speeds? The answer is 2:1, C. Start from VRMS equals the square root of 3 kBT over M. Same temperature on both sides, means VRMS is inversely proportional to the square root of mass. So quadruple the mass and you take the square root of 1/4. That means it's a factor of 1/2. So the lighter gas moves twice as fast as the heavier one. 2 to 1. Question 4. Now, the Maxwell-Boltzmann distribution. You are heating up a fixed sample of gas. Same molecules, just hotter. Curve 1 is before, curve 2 is after. So two things change. The peak shifts and the shape changes. Try to predict both before peaking. So what do you think? Of course, C, the answer is shorter and wider. Heating shoves the average speed. So the peak slides to the right. Easy enough, but here's the part that catches people. The area under the curve is the total number of molecules, and that has not changed. So if the curve speeds out, which it must because the speeds are now more varied, it has to drop in height to keep the area constant. So wider necessarily means shorter. Conservation of molecules forces the squish. Question 5. Two different gases now sitting at the same temperature. Gas X's distribution peaks at a low speed. Gas Y's peaks at a high speed. What can you say about their masses? The answer is A. Gas X is heavier. Same temperature means same average kinetic energy. And kinetic energy average is 1/2 mv squared is the famous equation. If gas X is shuffling along at lower speeds, the only way it can carry the same energy is by being heavier. So mass and velocity squared trade off. Heavy and slow, or light and fast. So the slow gas is the heavier one. Question 6. Here's a sneaky one. Helium atoms are zipping along at 1,200 meters per second. Radon atoms are crawling at 400 meters per second. Bring them into thermal contact. Which way does heat flow? So the answer here is, of course, from B to A, so B. Your gut says from the fast one to the slow one. But temperature doesn't track speed. It tracks kinetic energy, which is 1/2 mv squared. So helium is 4 times 1,200 squared is roughly 5.76 million units. Radon is 222 times 400 squared is about 35.5 million. So radon's atoms are slow, but each one packs 6 times the energy of a helium atom. So radon is hotter, and energy flows from radon into helium. So mass matters too. Question 7. Now imagine an insulated cylinder with a piston, and you slam the piston down fast. The gas inside heats up. That's a diabatic compression. Fine, but why? Mechanically, Where do the molecules suddenly find extra kinetic energy? The answer? A. Molecules rebound faster. Think of one molecule heading toward the descending piston. In the piston's frame, it bounces off elastically, same speed, opposite direction. But the piston is moving. Hop back to the lab frame, and the molecule's outgoing speed picks up roughly 2v piston extra. Every collision with the moving wall adds a little kick, multiplied by trillions of collisions, and the gas heats up. Compression literally speeds up the molecules through bounces.